Hey everyone, and welcome to the first video in this new series of physics videos focusing on condensed matter physics. So in this video, we are going to be introducing the topic of condensed matter physics. What is it? What does it apply to? As well as just setting the scene for everything that we're going to cover in the future. So going through some of the basic concepts that will come up time and time again. So I really recommend getting to know the contents of this video very, very well, because a lot of these concepts will come up quite regularly. Now, condensed matter physics is a pretty useful part of physics to understand. It can be a little bit counterintuitive when you're first getting into it, but it's actually a very tech-focused piece of physics. So a lot of the physics we will be covering in this series is actually got a really important historical context as regards the rise of semiconductors, which obviously fueled the rise of the technological age, but also things like solar panels and batteries and stuff. A lot of the physics which undermines this is actually condensed matter physics. And so unsurprisingly, it's probably a very good piece of physics to get to know if any of you guys are thinking of getting into technological innovation, because understanding the physical principles would be very, very beneficial in order to advancing the world as we know it, which is really cool. So with that out the way, let's go ahead and jump into the first topic in condensed matter physics, which is just having a look at some of the basics of crystal structures. So the first thing we are going to define in condensed matter physics is the word crystal. Hopefully you guys are familiar with the word crystal, but in physics it has a precise meaning, and what it essentially refers to is a regular structure of atoms. So all these circles I'm drawing right here are atoms, and a crystal structure is a structure where the atoms are arranged in a regular pattern. And this is a crystalline material right here. You can refer to this as a crystalline material. So where the atoms are arranged in a regular repeating pattern that repeats throughout space. So that's what a crystal is. And from this crystal structure, you can actually go ahead and not think about the atoms for a sec, and just think about the positions in space at which these atoms are located. So what I'm drawing right here are not atoms themselves. They're not sort of any sort of matter or anything materialistic. These are literally just positions in 3D space. And these right here are referred to as lattice points. So the lattice points, this would be an individual one, is a position in 3D space where an atom is attached, you can think of it. And this kind of whole array is generally referred to as the lattice structure, or just the lattice, essentially. So you have your kind of array of lattice points in space, and then you have an atom right here, which is attached to one lattice point right here to generate the crystal. And it doesn't necessarily have to be an atom, it could actually be a molecule right here. So you could in fact have a molecule that is repeated throughout space. But of course, each molecule is attached to an individual lattice point. So we refer to the thing, whether that's an atom or a molecule, that is attached to a lattice point. This is referred to as the basis. So it kind of makes quite good semantic sense. You can just kind of think of it as the basis for the crystal structure. But essentially a good kind of thing to bear in mind is that lattice plus basis is equal to the entire crystal structure. So you've got your basis right here, which is your molecule or your atom, and you've got your array of lattice points, your lattice structure. When you attach a molecule to every single point within the lattice, you produce your crystal structure right here. So that is the basics of what a crystal structure is. It's comprised of lattice and basis. Now what we're going to do is we're going to draw out our lattice structure right here, and we're just going to make a few more definitions. Now what you can do is you can essentially sort of see that if you join together adjacent lattice points, then you can in fact create a cell right here. And then you can see that if you repeat this cell pattern throughout the lattice structure, then you'll get an array of cells as well as like your array of lattice points. So this right here is what you can call the unit cell of the crystal structure. It is the cell which you can generate by joining together the adjacent lattice points. So obviously I've just drawn a simple square lattice structure right here. But just as another example, of course, you can have a 3D lattice structure, slightly harder to draw, of course, but what I'm drawing right here is a cube. And this box right here, this would be your three-dimensional lattice cell. So that is what a unit cell is. Now, the thing about unit cells is the choice of lattice points, which you can choose to combine together to create the unit cell, is kind of a little bit arbitrary. So what you could do is, rather than just combining together adjacent lattice points, you could in fact choose to have a unit cell, rather than made like that, is actually circulates around the lattice point. And then you could also do the exact same thing and kind of tessellate this this cell across, and you'd still end up with a unit cell. So we have to be a little bit more specific when we're talking about unit cells in terms of how many lattice points it encompasses. So now we come on to the concept of primitive cells. And a primitive unit cell is a unit cell which only encompasses one lattice point in total. So the two unit cells that I've drawn out so far are both primitive unit cells because in both instances they encompass one individual lattice point. So in this case, it's quite easy to see that there is one lattice point that is in the center of each unit cell. But in this point, it's a little bit trickier, but actually, if you kind of like maybe if I draw this a little bit larger, or say, here's your lattice point, and here is your walls of your cell, which you've constructed, you can kind of see that within the cell region right here, there's kind of a quarter of a lattice point right here. And so when you multiply each of these quarter of a unit cells in each of the corners by 4, then you get one lattice point within that unit cell. So that still passes as a primitive cell. But if I were to choose, say, this as the unit cell, which technically I could repeat throughout space and it would tile very fine, it wouldn't be a unit cell because it would encompass more than one individual lattice point. So in this case, it would actually encompass this one right here. And it doesn't really reflect the symmetry of the lattice pattern, unlike with this cell. So primitive cells contain one lattice point, and they reflect the symmetry of the cell so that when you replicate them throughout the crystal structure, they will produce the crystal structure. So in this video, I'm not going to go into too much detail regarding the different types of lattices, but I will just kind of illustrate a few different examples of two-dimensional and three-dimensional primitive unit cells. So in two-dimensional, I've only drawn a square lattice so far, but of course you could have a rectangular lattice, which has two different side lengths. So you've got this side, which has one length, and this side, which has another length. And you can also have sort of isometric unit cells. So obviously, if you've got your isometric lattice, this will have a unit cell which is actually a parallelogram right here, rather than a rectangle. Now, you might think that the unit cell might be a triangle, but in fact, you can't really tessellate this exact shape throughout space, because if you put that there, and if you keep kind of tessellating that throughout, you actually kind of miss half of the area within the isometric grid. So the triangle is in fact not the unit cell. It has to be a four-sided quadrilateral, particularly this is if you're in 2 dimensions. So your unit cell in the case of an isometric grid will in fact be a parallelogram. Now in 3 dimensions, you actually have many different types of primitive cells, but there are 3 in which I'm going to highlight. So obviously so far I've mentioned the cubic cell. So obviously now we're in 3 dimensions, which means that obviously a little bit hard to draw the kind of front-back axis. But this would be our kind of cubic unit cell within a cubic lattice structure. And this is actually referred to as a simple cubic structure. And the reason it's called a simple cubic structure is because there are 2 additional cubic structures, which I'm about to come on to. So the first of which is called the face-centered cubic. And this looks like the same as a simple cubic so far. However, the notable difference here is that as well as the 6 vertices, you actually have a lattice point which is on the center of each face. So you can almost imagine this as a dice which has 6 1 faces on it. And obviously in this case, the nearest neighbor, the nearest lattice neighbor, will actually not be the one which is on the same vertex of the cube, because of course the lattice point that is on the center is actually going to be the nearest. So you're actually going to end up with a structure once you kind of join them all up that looks a little bit like this. So as you can see, it gets a little bit tricky to draw, but essentially what I've done is I've connected every single lattice point that is on the center of the face of each side of the cube, and I've ended up with the face-centered cubic structure. And the last one is the body-centered cubic structure. And this is very similar in a way to the face-centered cubic. However, rather than having the additional lattice points on the surface of the faces of the cube, you actually only have one additional lattice point, which is right in the center of the cube. So this is at the halfway point in all 3 axes. And so as a result, you're going to get a lot of diagonals coming out from the vertices into the point which is at the center of the cube. Essentially, yeah, that's the body-centered cubic. And that is the last of the 3 cubic types of crystal structure. So all of these are kind of like the main ones that you'll encounter a lot of the time in condensed matter physics. We're not going to spend too long talking about different types of crystal structure, which is why I didn't really want to spend a huge amount of time on it. Most of the physics kind of is very applicable regardless of what type of crystal structure there is. But that's essentially just a kind of brief overview of that. So what I'm going to do now is I'm going to redraw out our lattice structure. I'm going to draw it out a little bit bigger this time. I'm going to keep to 2 dimensions for now, just because it's a little bit easier to draw, although all of this is applicable in 3 dimensions. And I'm going to go ahead and draw out the unit cell. I'm going to choose this as the primitive cell. So of course, what I can do is I can label this distance right here between lattice points. I'm going to call this A right here. So this is probably one of the most important parameters of any crystal structure. A is essentially the lattice constant, and this is defined as the length between adjacent lattice points. But in condensed matter physics, what we like to do is we actually like to use vectors, being the physicists that we are. And so what we actually do is we define a position vector, which is also called A, as being the position vector from, say, this point, if we take this point to be the origin, and this point right here. And of course, being a vector, it not only has the magnitude, so which in this case would be the actual physical length, but it also has the direction as well. And this is sort of saying that it's pointing, if we draw ourselves a set of axes right here, if we call this the x-axis and this the y-axis, we say that this A vector is actually parallel to the x-axis. So it would have an x component and no y component. And we can also give this side a length right here. So say that this side is of length b. Now obviously if this is a square lattice, then A would be equal to B. Then your position vector in this case would be vector B right here. So A vector would be the length of A times the x hat direction, and vector B would be the length of B in the y hat direction right there. So this is writing our lattice cell in terms of vectors. And this is something that we're going to see a lot throughout this course. And so obviously, like I say, in the case of a square lattice, A is equal to B right here. But of course, in a rectangular lattice, then A would not be equal to B right here. And so another example is if we have our isometric lattice, what would our lattice vectors be? Well, like we said before, the unit cell would be a parallelogram. This would have two different side lengths, A and B, yet again. So obviously if this was a rhombus, then A would be equal to B, but more generally speaking, it's a parallelogram, very similar to how if like rectangle versus square. So our two vectors would be A going along right here, and B would be going along down here. So that would be our two lattice vectors. And of course, in this case, if we still have our x and y axis, and x is along here and y is along here, then B would actually not be parallel to the y-axis. B would actually have both an x and a y component. But the key thing about lattice vectors is that you can get to, and this is a very key point, you can get to any position in the lattice by using a combination of both these individual constituent lattice vectors. And so that's a key point. And we can actually write this mathematically as if we wanted to do a translation, this would actually be equal to a sort of number, an integer number multiplied by A, plus another integer number, which we're just going to call u and v, multiplied by the B vector. So this is quite an important result. This is essentially saying that you can get to any point in the lattice using a linear combination of A and B. So say if I wanted to get here, I would be going along the A vector once, twice, three times, and we'd be going along the B vector once. So this would be our kind of T right here. And of course we can decompose it in terms of A and B. And the final thing I want to talk about is what is the area of a unit cell. So obviously in the case of a square lattice, or indeed a rectangular lattice, we can see that the area of the cell would be equal to this length multiplied by this length right here. So the area is equal to A multiplied by B, base times height. Very, very straightforward. But what about in the case of an isometric lattice? Well, obviously in this case, this would be the area of a parallelogram. But of course, the area of a parallelogram is this width multiplied by this height right here. And of course, this distance right here is not necessarily the same as this distance here. It would only be the same if it was a square and this angle was 90 degrees, which in a parallelogram, it is not. So how do we sort of more easily kind of calculate this? Well, this is where the vectors actually come in, and this kind of nice vector notation comes in, because we can actually write the area as being equal to the cross product of vector A crossed with vector B right here. So of course this would be equal to, if we were to expand this cross product out, the magnitude of A times the magnitude of B multiplied by the sine of angle theta, where angle theta is essentially the angle that is made between the two vectors right here, angle theta. So this is quite an important result right here. This tells you how to calculate the area of a unit cell. You take the cross product of your two vectors, your two translation vectors A and B in 2 dimensions. And if you know the angle between them, then you can simply multiply by A and B multiplied by the sine of the angle in between them. So that's good. And one last thing I'm going to touch upon is, of course, area is a 2-dimensional thing. So what would be the equivalent in 3 dimensions? Well, this would be the volume right here. So rather than talking about the area of a square, we're going to be talking about the volume of a cube in this. If we're going for a simple cubic primitive cell, then we would be going for the volume of this cube right here. And of course, since we have 3 dimensions, we actually have to add an additional vector right here. So rather than just A and B, we're going to have A, B, and C right here, where of course we're in 3 dimensions, so therefore we now have a Z-axis as well. So how do we work out what the volume of this cube would be? Well, like in the simple case of the square, we can simply write that the volume of the cube is equal to A times B times C. So rather than in the case of a parallelogram in 2 dimensions, the 3-dimensional variation is what's known as a parallelepiped. And this right here is essentially within our sort of 3-dimensional isometric grid right here. It's a parallelogram, but it's in 3 dimensions rather than 2 dimensions. And so we're still going to have our 3 vectors A, B, and C right here. And in order to work out the volume of this parallelepiped, we actually do what's known as the triple product. And the triple product can be written in terms of A, B, and C as A dot producted B crossed with C right here. And you could actually write this out if you wanted to, although I don't normally see this being done, as A, B, C times sine of theta, where theta is the angle between A and B, multiplied by cos of phi, where phi is the angle between A and C. So obviously it's getting a little bit messy right here. Phi is the angle between vector A and vector C, and theta is the angle between vector B and vector. But I've not really seen it written like that very much, but it's just good to bear in mind right there. So that's how to work out the volume of a parallelepiped, which is the 3-dimensional unit cell for an isometric lattice structure. So that brings us to the end of this first video on condensed matter physics. Like I said, I've just kind of gone through and defined a whole load of really useful quantities, both semantically and mathematically. And now that we've done all of that, now that we've got the basics underway, we can go ahead and really start like proper physicsy stuff. And yeah, so hope you guys have found that really helpful, and I will see you guys in the next video. Take care.